Hi, my name is Jan Lagervall, and I am the corresponding author for the paper Liquid Crystal Elastomer Shell Actuators with Negative Order Parameter that will be published in Science Advances on the 12th of April 2019. Life can get pretty messy sometimes, and we might wish that somebody would tidy up the disordered state that we end up in. Also in nature, disorder is common, for instance in an ordinary liquid like water. The molecules move around randomly in a disordered fashion. But if we cool down the liquid, what we call a phase transition to a crystalline solid state can take place. And almost like magic, the molecules arrange regularly all on their own in a perfectly ordered state. Whether it's about cleaning up a mess or understanding changing behavior in nature, or about designing a material that should be really strong, it is useful to measure how ordered something is. If the order concerns how well molecules or other items are aligned, this is done with this equation, which defines the so-called nematic order parameter. The angle beta is the angle between any individual molecule and the average alignment direction. The term nematic comes from the most common liquid crystal phase. But what is a liquid crystal and where do you find it? Well, the supermaterial Kevlar is so strong because it is produced from a liquid crystalline state. You can even find liquid crystals within you because the membrane of every cell in your body is a liquid crystal phase. And perhaps you heard the term liquid crystal display or LCD? Well, that tells you that the active material in your laptop or TV display is, if it's an LCD, a liquid crystal. In a nematic liquid crystal, the molecules are disordered in position, as in ordinary liquids, but they have orientational order, meaning that they line up more or less along a single direction, as in this bundle of spaghetti. If we let the spaghetti fall down on the table, we get a disordered state, right? Well, actually not quite. It looks disordered from the top, but if you look from the side, you'll see that the spaghettis are actually very ordered in the sense that they are all in the plane of the table. But in that plane, they are indeed disordered. We could say that the spaghettis avoid a certain direction, the direction perpendicular to the table. The nematic order parameter actually captures also this anti-ordered state, and this is the state with negative order parameter. Until our work, a liquid crystal with such a ground state was never found. Instead, liquid crystals normally have a positive order parameter of about S equals 0.7. You can heat the liquid crystal to a regular isotropic liquid, where the order parameter is 0, as it should be for a completely disordered state. But a liquid crystal that spontaneously adopts negative order? Well, that was as hypothetical as is a perfectly ordered liquid crystal, where all molecules would align exactly along one direction with an order parameter S equals 1. So, how did we succeed in making a liquid crystal with this negative order parameter anti-order state? Well, as you can see, we are serious scientists, so we put on our lab coats, wore our goggles and our gloves, and we went into the lab. There, we blew up balloons made of the liquid crystal. Of course, the liquid crystal balloon was a bit different and a lot smaller, and we inflated it by pushing in liquid instead of air. But the principle is not so different from blowing up a party balloon. So why is this expansion so important? Our liquid crystal balloon, which we call a shell, is actually a rubber, just like the party balloon. Before inflating, the shell is thick and the molecules are disordered. When we inflate it, the rubber has to stretch in all directions in the shell plane, and the molecules then have to orient into that plane. But in that plane, they can point in any direction, just like the spaghettis on the table. This is how we get the negative order parameter. What makes our liquid crystal rubber shell a bit different from the party balloon is that it can actually do this order chain on its own without us inflating or deflating it once we have prepared it. All we need to do is cool or heat it. If we cool, we get the anti-ordered negative order parameter state, and if we heat, we get the random zero order parameter state. And because this is a rubber, the shape has to change between thin and wide and thick and short. When we cut little slices from our shells, we could use this temperature sensitivity to make the slices change their shape. This is why they are called actuators, or artificial muscles. Not too far in the future, we hope to put these actuators to use in robots that are soft so they can interact nicely with humans. Thanks for watching. You can download the paper without any subscription from the Science Advances website.